Good morning, folks. It's a cold morning here in Scotland. It's Sid here from Border Archery. I wanted to try and cover a video on how I would assess a bow and give you some of the reasons and logic. So somebody hands me, there you go, there's a bow, right? What do you think of it? Well, first off, straight off from looking at it, it's got deflex. That's good. Yeah, I like that. The bracing is quite low. Okay, so it's got energy, but it still has shape to the limb. Right, too much shape and you lose your vertical stability. Okay, so what I'm talking about is if I push the string up and pull the string down, how much movement do I get in the limbs? So if I push it up, let's see if I can hold it still, you'll see I can straighten that limb out. And if I push it down, I can put more bend in the limb. Okay, so that means how much does that knocking point want to wobble up and down? Some bows are atrocious. Yeah. Now, please bear in mind, and this is where I put a big caveat in. Okay, this bow, most of these tests are kind of draw weight dependent. Okay, heavier weight bows are generally more robust because I am proportionally weaker to them. Okay, so this bow in this example is an 8-pound bow. Now I shall prove it is an 8-pound bow. Okay, yeah, I lie, it's 12. Woohoo! Right, so the vertical stability of the bow. Okay, how easy is it to rock up and down? So first off, pick up the bow, you kind of look at it, do that, there you go, you get a rough idea as to what the bow's doing. Fine, okay. Let's have a quick, see, I just grab the limb tips. Now, what you're looking to do is you're looking to rotate the tip round, okay? So, does it twist? Yeah? Right. Now, our bows are torsionally stiff. We're famous for it. We invented this aspect of it. It's also quite a big recurve, so you've always got to look at how big the recurve is. So it's easier to move. It's a really big long lever. It's quite short. Should be harder to move. Some of them aren't. Okay. So this one feels particularly odd because it wants to go backwards and forwards in comparison to left to right. For the amount of work I'm doing, it's only a 12-pound bow, remember. Yeah. So, okay, so then I can have a feel of the string tension. Yeah, string tension. Yeah. So, I'm just going to take a rattle. Okay. Yeah, you can feel the string tension. But there's one, where did I put this? There's one part to testing a bow which is quite good fun. And it works for recurves. Like, I'm talking kind of good recurves. I'm not talking something like a long bow with a 1-inch hard static tip to it. I mean, that's not really a recurve, right? So, draw length, measurement arrow, tape measure, doesn't really matter, okay? But what you're looking to do is pull the bow back until the string lifts off the very last part of the recurve there. You can see it, okay? So just about there, measure the draw length, okay? Now, what that part means is that when you look at a draw force curve, right, you get the bulge and then you get the stack, okay? So you get preload in a convex curve, and then you get stack, a concave curve, okay? And the part where the graph changes, right, that part where it changes, called the inflection point, for a good recurve, that's where it is, okay? That is because it's where the draw length is shortest, but the limb length is longest, okay? So the lever is easiest to bend, but the draw angles, etc., the geometry of the setup is most favourable for smoothness. Okay, so you measure where that is. So For most traditional recurves, around about 19, 20 inches, might even get to 21. Now, the reason why it would get to 21 is because the bow could have parallel cores. Okay, so what you do is you have a quick look here, thickness here, and then you get down to this end, you have a look here, and you can see whether it's got a parallel core or not. Now, the parallel core would make the recurve static-ish, whereas a tapered core makes the recurve work. Now, what I mean by work is the recurve will straighten out as you pull it back, whereas some bows will keep that shape. Now, the reason why it will keep the shape is because it will defend, it'll stop it. See, look, it's opening out, and as soon as it opens out, that string, the string will lift, which means if it keeps the hard shape, then that lift point will be further out in the draw. The downside to having a more static recurve is the outer part of the limbs, the heaviest, which is the part that's most dynamic. Yeah. Now, if somebody's handed you a bow, there you go, what do you think? Yeah, vertical stability is good, got T-flex, yeah. So, quick look down through the middle of the bow. Oh, there's quite a lot of over centre. Oh, that's good for clearance, that's good for tunability. Well, there you go, there's a bow. So, you could, if you wanted, by getting back to about 3/4 draw, hold on to the bow, give it a push forward, give it a push back. How stable is it at full draw? Yeah. Remember, draw weight dependent. So the more bows that you do this with, the more you'll start to be able to assess bow design. Yeah. So there's one test that I haven't done here because the bow's strung, because somebody just handed me the bow. Here, assess that. But one thing you can do is you could take a grain scale. I'll take a piece of aluminium to mimic the grain scale, okay? And you take the limb unstrung off the bow, the limb itself, and what you would do is in the middle of the pad of the grain scale, you'd put the limb on a table, creating a bridge, and you'd measure how heavy the tip was, yeah? And it was in 65 and 80 grams of weight is kind of normal, right? So this end would be on the table, creating a bridge, and the bridge would give you the weight on the end, okay? That kind of gives you a rough estimate as to how much R&D the company's done in getting a lightweight limb, right? The lighter the limb, the faster, more efficient the design will be, because it's not having to accelerate all that weight. For example, if that tip weighed the same as the tip of a hammer, you'd end up with a lot of hand shock, and also the limb would be slow to get that hammer weight moving. Yeah. So the lighter that tip is, the more efficient the design will be. Now, efficiency is a very strange term. Efficiency is something that people brag on about, and I think efficiency is a bit of a weird misnomer. Let me try and go into this one. It's something that was said in another prominent archer's video when he was comparing two different models. One bow was 4 feet per second faster than another one, but the energy you had to go in to get that meant you end up with more fatigue at the far end. 4 feet is roughly 2 feet per second per pound of draw weight. So on that bow that he was said was using up more energy, drop 2 pounds in bow weight, right? You won't have the fatigue issue, but what you will be doing is pushing the same arrow at the same speed as the other one. You'll have the same energy, you'll be doing the same amount of work, but you'll actually have less weight on your fingers, which brings up an even more complicated concept, right? Anatomically, right, how we work is that this part here, right, this part of the draw, you want it loading up heavy, you want it getting the work done then, yeah? Because you spend very little time there, right? You spend all the time back here, you'll spend it here whilst you're getting all your concentration done and concentrating on getting through the clicker, right? So having 2 pounds less in your fingers whilst you're concentrating your clicker is a really good thing. But anatomically, if you were to do every millimetre of draw takes exactly the same amount of time, and it takes the same amount of effort to achieve that bit of draw length, then yes, I would agree that fatigue's the issue. But it's not quite like that, because you're using different muscle groups, and the different muscle groups for the control at full draw are the different ones than you use when you first start to pull. You guys can test me out on this one. You guys can go and do your research and find out what muscle groups you use at different parts of the draw. But the fun bit is that the amount of time spent at the different draw weight stages of the draw, you're actually anatomically better and more efficient getting the work done early, reducing your draw weight slightly, and fatigue doesn't quite apply the way it was implied on that video. Okay, so it's way more complicated than that, right? So, but back to the efficiency point. Efficiency is a bit of a weird one. Your main objective is to get arrow speed downrange, yeah? Arrow mass travelling at speed. The faster bow is mainly the objective, isn't it? The kind of the problem that I always seem to keep bumping up against is that when you look at the efficiency, so that's the energy in compared to the energy coming out, when you're comparing two bows, the energy out part of the equation is mass and speed. Okay, so what we do is we keep the mass constant and then compare the variable side of speed, so that we're comparing like for like. That's really unfair, because the faster bow is going to be less efficient. If you have the same bow and you make it faster, it becomes less efficient. So speed is not efficient. I think it was Bugatti turned around and said that they had to put in something like 400 horsepower to get 16 miles an hour. Why? Why do you need 400 horsepower? 400 horsepower would achieve like 150, 160 miles an hour. So why do you need 400 horsepower to achieve 60 miles an hour more? Well, that's because drag is logarithmic. It gets exponentially harder. It gets more difficult to achieve the faster you go. It's like running into a brick wall eventually. So when you think that the faster the bow goes, the bigger the hurdle it's got to achieve to get that one little bit more, means that the faster bow is at a disadvantage. So rather than taking mass with the speed being the variable, what you should try and do is achieve the same speed through the chronograph, 190 feet per second, right? What does it take to get two bows of the same weight to achieve 190 feet per second? And then look at the mass as the variable. That way you're not hindering the faster bow for the efficiency stakes. And you end up with a several percent difference in percentage values when looking at two bows, when comparing the faster bow to the slower bow. Okay, so don't be fooled with people playing with statistics trying to disadvantage the faster bow, saying it's less efficient. It's less efficient because it's faster. Make them the same speed and it gets blowing close, right? Don't be duped by plonkers on the internet, all right? So check out bows, have a look at them, feel them, gives them a little bit of a poke, a bit of a push shove. Check out where that smooth point is, right? The closer to your face, the less the stack's going to start to come in, okay? So you can look at it. Now, what that test will show you is that cheap 150 quid limbs with a parallel core can be smoother than the more high-tech top-end limbs that have got a taper, right? And that's because the parallel core holds the damn thing together. And the twist in the tail for you guys is that sometimes the cheaper limb is sometimes the faster limb. It depends on the mass, okay? Now, the parallel core will have a heavier limb mass because it's all out here. The thickness is still there. It's heavy here, right? But because it's smoother, it quite often has more energy, which means that the cheap limbs with the parallel core can sometimes be faster, if not as fast, than the more expensive limb with the taper to them. Okay, and that's because they're using the same cheap formers to make the same cheap bottom end as they do using the top end, right? So that relationship of just pouring different ingredients in at the front end and ending up with a different thing at the other end, but the same process in the middle, that's the trick. That's the bit that's causing some of the fun. Now, technically, if you wanted to have the same smoothness point on a limb that works, you can afford to have a slightly bigger recurve because it'll open and give its recurve away, so you can start with a little bit more so that it's got it to give it away. That's the debate between static recurves, working recurves, and, pardon the pun, it's not a binary debate. There is semi-working. Yeah? With varying amounts of working, and then you can have different portions working. Okay? So don't get stuck with it. So those are the things that you're looking for: vertical stability, vertical stability, vertical stability, torsional stability. There is more complicated stuff in there, but yeah. So that's how I would assess a bowl. All right. Hope that helps. Hope that adds to some people's thinkings. But what I would recommend you do is take hold of ILF. It's all the same bland, homogeneous stuff, right? Everybody makes the same stuff. And a point my dad always said, sorry for this, off topic. My dad always said, right, you've got two companies, okay? They both make one washing powder each, okay? They've got 50-50 market share, but one wants to grow. How do they do it? Well, they take exactly the same product and they just bring it out as another model, okay? So we've now got two soap powders from one company. So they end up with 2/3 of the market, the other one ends up with 1/3 of the market, and I want my 50-50 back, says this guy. So he ends up coming out with two soap powders, okay? You get soap powder A, soap powder B, the same damn product, but they're now marketed differently, but they're exactly the same item, so they get 50% of the market back. If the other company comes out with a third brand of the same stuff, then what happens? He doesn't get such a big chunk. There comes a point where you end up limiting your progress. Okay, so now you know why, in my opinion, why you've got so many different brands. So you've got like 5 manufacturers with a top, middle, and bottom, and then each one of them then starts to sub-break out. And we've seen that before. We've seen companies come out with new companies, but it's still the same original one. Yeah. For example, Volkswagen also got Audi and Skoda and other brands. Yeah. But it's actually the Volkswagen Audi group owns Skoda as well. Right. Well, it's damn same implement archery. We've got one company makes 3 brands of limbs, and within that 3 brands of limbs, you've got a top, middle, and bottom. Subdivisions of the same stuff. Don't be duped by it. Have a look at it. Stop reading the marketing and actually look at what you've got in your hand. Things like the limb tip shape generally gives away that they're coming from the same manufacturer because they've got like a CNC machine that just sits and grinds off the tips. All right. Anyway, thanks for watching. Any comments? Ping them below, and I'll do my best to answer. And sorry for the off topic, but there you go.